So, we were doing statistical physics of phase transition. Okay. In that background, I discussed systems, in fact spin systems, where phase transition occurs, but what happens during the phase transition. Okay. That is what we are after. Okay. During the phase transition, it turns out some parameters change with scale. Okay. We will see that like mass in field theory changes the scale. So, parameter of the field theory will, if you look at one scale, it is a number, but when you go to larger scale, then the number changes. Okay, that is called renormalization. Okay. So, renormalize means how the parameter is changing with scale. Understand? No, scale is okay. So, idea is, well, I did discuss about fractal, but if you look at human body, so human body, I see, you see this scale, but you go inside, then you will see heart or intestine. So, in fact, your parts are changing, but just think of a homogeneous system like gas in this room. At a larger scale, we have temperature, but you go down, you get the same temperature, right, as long as you do not go to microscopic scale, atomic scale. So, this is how you should see, how I am going to see the system changing with scale. Okay. So, I did some of it, but let me recap this description of renormalization group. So, renormalization means how does a parameter change with scale, renormalize, how it is renormalizing, adjusting. Okay, that is what is parameter changing. Okay. So, this field renormalization is used in lots of fields, particle physics, condensed matter physics, statistical physics. So, these are the names in statistical physics. Okay. So, this is a picture of Wilson who won the Nobel Prize for this work, but renormalization is became famous by the work in quantum electrodynamics, when the mass of electron renormalizes, right. I mean, I did discuss some of it as a very crude way in earlier lecture. So, we will do that. I am going to show you how mass changes, mass of electron changes with scale. Okay. But let us, so this is a, I mean, what I am going to describe is most clearest explanation of why parameters change. All right. So, we start with spin system. So, we have spins. I did this in previous lecture, but I am repeating it because it is a long time before we did that. So, we have spins at every site, is a square lattice here, it could be cubic lattice too, or it could be 1D lattice. Okay. Depending on dimension, we will have neighbors. Now, so we apply mean magnetic field H, external field. So, Hamiltonian or energy is minus beta H, minus sigma dot B, right. So, this H times spin, total spin, that is energy, right, external field. So, this is due to external field, and this due to interaction among spins, and this coupling is well, in most systems it is nearest neighbor coupling. So, this spin here is interacting with neighboring spins, the 4 of them at the faces. We do not think of diagonals or the corners. So, this spin x is interacting with 4 spins, this spins, and if you put in this system, this called Ising spin, this shows very interesting behavior called phase transition. Okay. So, at high temperatures it is in a disordered phase, T greater than T critical, but at T less than Tc it is in an ordered phase, it could be either up spin or down spin. Okay. This is a phase transition. So, this system has been studied by lots of people, very smart people. So, it turns out this system which I described has been solved in 1D and 2D, but it turns out that at the large scales, so that was a atomic scale, basically spin scale, but if you look at coarse grained scale, so we have spins here, spins here, spins here, but if I look at these big scales, big spins, big spins, big spins here, then we can make a continuum. So, here if I average over many spins, I will not get discrete numbers, right, 50 spins positive, 30 spins negative, it will become continuum. And so this is the field which I described phi of x. This is sum of all the spins in neighborhood of x, okay, this continuum, the way we talk about fluid velocity, because this velocity is sum of velocities of all the molecules in a region, and it is continuous variable. So, phi of x is treated as continuous variable, and it turns out all the properties of phase transitions, well, lots of properties, I can say all, lots of critical properties of phase transition can be described by this free energy. Okay. So, this is Wilson's idea, well, many people, but Wilson kind of I think is given credit for this, leading credit for it. Okay. So, he says the property of phase transitions we can understand by solving this, basically using this free energy formula. Interestingly, the phase transition properties of Ising spin is very similar to phase transition properties of liquid to vapor transition. Okay. Because both of them can be described by the same equation at large scales. At small scale, of course, they are very different systems, but the phase transition property depends on this equation. Okay. So, this is, that is why it is called universal theory. Whatever details at small scale do not quite matter, at large scale this equation is works for theory of phase transition. Okay. So, analogy is, of course, this R naught is like m squared. So, we have done this equation before phi 4, this we called it phi 4 theory, this H phi was not there, but this is the term coming from the magnetic field, okay, external magnetic field. So, this is called phi 4 theory. And so, this is grad phi squared, and C naught is a constant, U naught is a constant, m squared is a constant, but I am going to use R naught, okay, and I will follow this book Copid's notation. Okay. So, he showed the small scale do not matter, and we can get a universal theory of phase transition. I am going to explain that in today, and I think we need one more lecture, then that will become clear what is the theory of phase transition of Wilson. Okay. So, RG procedure. So, RG procedure, so there is one, well, it is basically it involves two steps, one thing is called coarse graining, other one is called rescaling. Okay. So, we have lot of spins. So, at every point there will be up or down spin. Now, we make bigger boxes, right. So, each of these box has 16 spins, right. So, this box has 16 spins. So, earlier they were small boxes, right, this is tiny boxes, each box had one spin. Now, we have box with 16 spins in each box. Okay. So, you sum up the spins for the 16 spins, I mean you make an average and give one spin number for that. You can add them up. So, let us say 8 plus and 8 negative, then you will get 0, or 6 up 9 down, well no, 6 up 6 9, yeah, 6 7, okay, 15. So, 15 minus 9 down will get minus 3. So, you get a number. So, you put numbers here, these numbers. Remember earlier it, so this is what is put in here, okay, this put the numbers. Of course, the spins are interacting with each other. So, the interaction between these spins, so the 4 interaction, no? This, if you focus on this spin, the interaction 4 spins here, and they are all J's, microscopic interaction. But when I coarse grain it, what is the interaction between this spin with its neighbors? Will it be J or will it be different? Okay, it will be different number. So, you can say that this J prime, but this is at level 1. So, you can call it J1. Okay, so, this is after doing the coarse graining. Now, once you have done coarse graining, this here the grids, well, right now, well, I should not go there actually, I should not write it here. The two steps, just focus on this box, interaction between these. I should have made the interaction between this one, this, and the 4 of them, but the distance is large, right. So, just focus on the left one, don't go to the right. Now, the distance is more, right, for the neighbors, the in fact is 4 units. For the axis here, the neighbors are 4 units apart, but of course, the spin is bigger number. Okay. Now, we do the next step is called rescaling. So, I want the same 1 unit distance between two nearest neighbors. So, scale by factor 4. So, this B will be 4. So, this 4 unit distance will become 1 unit distance here, this is 1 unit, 1 unit, 1 unit. Okay. So, now we look at what happens to coupling constant J. Is it J or something different? We can call it at this level J1. So, it has 2 steps, one is coarse graining, other one is rescaling. So, J goes to J1. So, this is called renormalization. Next step, what will I do? I make this box a 4 again, this box, another box like this. Okay. And again you make a average, 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 and get some numbers, then again do the rescaling. So, from J1 it goes to J2. Okay. So, we keep doing this operation, and this operation is called renormalization. So, operation is renormalization, but under operation this parameter J is changing to J1, J1 to J2 and J2 to J3 at every level. Okay. So, whole thing is this is the process of renormalization. So, this is under scaling. So, symmetry we are exploring, study of symmetry under scaling. Scaling means going to small scales right now here. Now, you have understood, you have thought of symmetry about rotation, space translation, but these are different symmetry. You are coarse graining, well, we are going to different scales. Okay. So, okay, this operation. So, symmetry is understood. Symmetry is normally studied using group theory.
How do we know these operations are symmetry?
This is how I am defining the symmetry operation. So, what is the rotation group? So, if I take this system and I rotate by any angle, no. So, if object is symmetric under rotation like this object looks symmetric under azimuthal rotation like that. So, any angle rotation by any angle is an operation. Okay. So, we have rotation theta, this is operation, and if the object remains unchanged during this operation is called, this object is symmetric under rotation, understood, and r theta is a group member. You also know that r theta 1, r theta 2 equal to r theta 1 plus theta 2, right. So, this call, if I multiply I get a rotation by a bigger angle theta 1 plus theta 2. Okay. So, these are group properties. So, for rotation or for group, these are the, well, I think before I go to that, let me just give another example. Before I go to groups, this is another example. Okay. So, we have individuals in our country. So, that is one level, you are looking at individual level, individual interaction, but I can make coarse graining. Okay. So, I can make a bigger boxes, then I do not have individuals, but I have societies or group mohalla, so group of people, and then at that level there are interactions, there are certain properties, you can say income or some properties. So, I get this, these are not individuals, these are groups of people. Now, we scale it. the distance between the individual this groups are is a bigger group. So, scale it, then you get this country in I will get the distance to be same as before between the interacting units. Okay. So, so we can go from individual level to group level, then group subgroups and group subgroups, we can keep going up. So, this operation, you have two operations, one is coarse graining and rescaling, and but finally, if the system was symmetric under this operation, India at this scale will look exactly like this scale, it won't look changed. Okay. So, if it is not symmetric, then you see something different. So, in the previous example, if j remains j, then this operation will, this system will be symmetric under the scaling operation. Okay. So, that is what we look for, is it symmetric or not symmetric. Okay. So, let us just state the group properties. So, group for so there are 4 properties a group has to satisfy. So, there are elements of group A and B are group, then A dot B is also in a group. So, for rotation r theta 1 is a group member, r theta 2, these are normally matrices, no, we think of matrices. Then r theta 1 product will be r theta 1 plus theta 2. So, if this is group member, this is group member, this is also a group member. Associative property. So, we have 3 angles, r theta 1, r theta 2, then you do r theta 3. This is equal to r theta 1, well first you do r theta 3, then do the combination, which is same as do r theta 2, r theta 3 together, then do r theta 1, it remains unchanged, no. So, this is called associative properties. For rotation we have identity, which is rotation by 0 angle identity, and inverse also. Okay. So, group should have a, for every rotation there should be anti-rotation, so that I get back the original object. This is symmetric, but imagine a cube. Okay. If I rotate by any angle, I will not get the same configuration. No? I rotate by 90 degrees, that is the thing. So, for a cube, if I rotate by minus 90, then I get back the same cube. So, every member should have inverse. For here, well, this is symmetric object, but well, this is not quite symmetric. In fact, this part will destroy the symmetry. So, at what angle? So, if I rotate right by 10 degrees, then to inverse of it will be rotation by minus 10 degrees. So, a group must have an inverse, okay, which takes back the object to its original configuration. Okay. So, does this scaling operation which I described, is it a group or not? So, it turns out this scaling operation, these 3 properties are satisfied. Okay. I scale by factor 4, then I scale by another factor 4, I will get scaling by factor 16. Associativity also satisfied, this identity which I do nothing, but its inverse does not exist. Once I have coarse grained it, I cannot get back the original. Okay. So, inverse does not exist, that is why scaling is not a group really. So, we will call it renormalization group, but that is incorrect name. It is really a semi group, because its identity does not, its inverse does not exist. Okay. So, we should really call, we should call it renormalization semi group, but this word has stuck with people. So, this is called renormalization group. Okay. Okay. So, what is the objective of renormalization group? So, we like to study how parameter changes the scale, okay, and this changing, well, this property of change or how things change with scale tells us very important property of the system. Okay. In fact, phase transition will characterize phase transition using this property, which will become clearer at the end of the lecture. So, this is called renormalization of parameters. I gave the example of perfume. So, this I think I did in the last class, I will not repeat it. So, the diffusion of perfume at small scale is different than diffusion of perfume at larger scale. Okay. So, these parameters, we will see that some parameters do not, well, some parameters under the scaling operation become small and small. Okay. So, these are called irrelevant variables, something which is not mattering. So, it is called irrelevant variables, and so the unimportant ones go to 0. So, these are irrelevant. It will become clear when I do the theory, and these are called relevant. The one which remains finite, in fact which may grow also, that is called relevant.